Your textbook sort of assumes that you're able to visualize or graph these functions relatively easily, but I don't think it's quite as clear as they would let you believe. So I wanted to talk just a little bit about how we represent these functions from different sets of R or different products of R to other products of R. Start with what your textbook focuses on, which is functions from R to R2 or R3. And typically these are parametric type equations. So we have something like f of t is equal to t times I hat plus t squared times j hat. This was an example they gave in the book. You could also equivalently write this as f of t is equal to t comma t squared, and that implies that the x-coordinate is determined by t and the y-coordinate is determined by t squared. Okay, so let's think about how we would plot this just for a second. The easiest way to do it, and just like when you first learn functions, is to make a short table of values. And we can do that. We can just say we have some value of t, then we have our x-coordinate, and we have our y-coordinate. And we'll just do a couple. Let's say t is 0. Well, then the x-coordinate is just t, which is 0. And the y-coordinate is just t squared, which again is also 0. So if t is 1, then the x-coordinate t is also 1, the y-coordinate t squared, again 1, not terribly interesting. Let's do 2, t is 2, the x-coordinate of t is 2, the y-coordinate t squared is 4, and let's do a negative value. Let's do, say, negative 3 for t, then x would be negative 3, and y would be 9. So if we plot those, what we're going to plot is really all we're going to plot are the x and y coordinates. Okay, the t value is just a parameter, and it doesn't actually appear in our graph. So the coordinates we're going to plot are 0, 0. I'm going to sort of fudge the units on this graph. 1, 1, negative 1, 1, 2, 4. But you get the idea that these are just the coordinates of a parabola. Okay, so here I have just some sort of generic equation, and I've got let's just put a couple points on it here. All right, and we'll label this point x1, y1, and this point x2, y2. Our function f of t1, let's say, gives us x1, y1, and our function f of t2 gives us x2, y2. And that's what we mean by a vector function. So that means that when t equals 1, we have some vector x1, y1, which we can represent by that particular vector. And then at t2, the vector, instead of pointing there, points to x2, y2. So really what happens is you think of these vectors, they're all vectors defined by t, and as t changes, the tip of the vector traces out the curve. All right, so let's take a look at a couple of examples. Okay, here's an example. The function f of t is equal to t I hat plus t squared j hat plus 1 over t k hat. You can see the representation up here in this box. It's represented sort of differently. It says just there's an x and a y and a z coordinate. Each one is a function of t. So x is equal to t, y is equal to t squared, and z is equal to 1 over t. And this just says that the parameter goes from negative 5 to 5. So it looks like a curve, just like a curve on a standard graph, but it's sort of traveling through space. So as we pan around, we can see some interesting features. If we look at it sort of dead on from down the x-axis, we can see that it's y is a function of t, y is t squared, so z is 1 over t, so it's some sort of transformation of the graph 1 over x squared. If we look at it from the y direction, or directly from the y direction, in this particular case, it looks pretty much like y equals 1 over x. And we're looking at it from the wrong direction, so it's negative x, but that's okay. And that's just because x is equal to t and z is equal to 1 over t, so z is equal to 1 over x. And then if we look at it again from the third direction, we see that it's just the parabola y equals x squared. So we've got all of these things, but if we put them together into this parametric equation, we get this sort of interesting curve traveling through space. In another video, I'll explain how to produce these graphs from vectors a little bit more clearly in 2 dimensions. So if you're still a little bit unsure about this, watch the next couple of videos. Okay. The next type of function I'd like to talk about is one that's not mentioned in your textbook, and that is functions from R2 to R or R3 to R. These functions produce a scalar. The output to these is not a vector. It's just a scalar. So we call these scalar fields, and the reason we call them a field is because what it does is it takes each point on the plane or in space and associates with it some value. And the easiest way to think about this is you could think of the temperature in a room as a scalar field. So maybe near the floor it's nice and cool, up near the ceiling gets a little bit warmer, and the temperature varies with the location in the room. What you would do in that case is you would essentially associate a temperature with this point near the floor, and then maybe some other temperature up here and some other temperature up here. They all have values. We're not going to connect these because every other point has a value also. So every point has some sort of temperature associated with it. So it fills the whole space. The function fills the whole space, and that's sort of why we call them a field. And it's a scalar field because it fills the whole space with scalars. Okay, so let's take an example and try to graph it. The scalar field I wanted to graph is f of xy is equal to sine squared x plus cosine squared y. So this associates with every coordinate point xy. It associates whatever value I get from taking sine squared x and cosine squared y and adding them together. First, let's calculate one or two values. So let's say I do f of 0, 0. Sine of 0 is just 0, so 0 squared is 0. Cosine of 0 is 1, so that's just 1. So f of 0, 1 is 1. Let's do f of, say, pi over 2, 0. Sine of pi over 2 is 1. 1 squared is 1. Cosine of 0 is 1, so 1 squared is 1, so we get 2. So we can just plug in different values, any pair, and for every pair we get a value. So the question is then, how do we represent that? So for sine squared x plus cosine squared y, you might try to represent it on a 2D Cartesian plane, and that's because you've got x and y, and that seems naturally 2D. The problem is the answer is not x and it's not y, so what do we do with it? Well, one way to do it and still stay in two dimensions is to do it with color, and that's what the program Grapher does, and it gives kind of pretty pictures, and let's take a look at that. So if I plot sine squared x plus cosine squared y in Grapher, it gives us this sort of heat map. And what the heat map does is it tells us that when it's blue, then the values are they're lower, and when the values are red, it's sort of higher. So we can sort of see we have peaks and we have valleys, and then we have sort of neutral areas in between. But like we see, this is a field. It's assigning some value, and then the value is mapped to a color for every point in the Cartesian plane. This is really pretty, and it does give you a pretty good idea of what's going on, but it's difficult to judge relative magnitudes. You know, how big is blue, or how small is blue compared to the big values of red, and what are these green values in between? It's sort of difficult to wrap your head around. So this isn't usually how we do this, although they do make for really lovely graphs. Alright, there are other ways to think about this, though. Instead of associating some color with the output value, we could associate a different coordinate with it, and that leads us into 3 dimensions. So let's take a look at that graph. If we wanted to graph z is equal to sine squared x plus cosine squared y, the same function, a function of two variables x and y, but in this case we're assigning the output to the value z, which would be our third coordinate. So if we graph that, it looks something like this. It looks kind of like an egg carton, to me at least, but we have a similar picture. If you look at it from above, we can see that we have the peaks and the valleys that we saw in the heat map version of this, but it just gives us maybe a little bit better view. The problem with this is that really we're assigning every point in the plane a value, and I think the heat map really reflects that very well. This sort of divorces us from that a little bit, but as long as you keep that in mind, you should have no problem. Alright, the last type of function that I wanted to discuss and talk about how to visualize are functions from, say, Rn to Rn, not Rn to Rm. For example, a function from R2 to R2, or a function from R3 to R3. Now we'll look at graphing both of those. They're slightly different, but what happens in this particular case is you take in a point, it maps a point to a vector. And if you remember from the first video, there is a subtle difference between points and vectors. And in this particular case, it becomes more apparent. But we take a point and we map it to a vector. And that means that at every point in the plane, we assign to it some vector. Okay, let's discuss a simple one here. So let's take a function from some point xy to the vector. Let's just assign it a constant vector, perhaps maybe 1, 1. Well, the vector 1, 1 looks something like this. The scaling is off. The length of it is not necessarily correct here, but here we have a vector 1, 1. Now that's at the origin, but really this is saying at every point we have the vector. No matter what x and y are, we have the vector 1, 1. So perhaps over here at 1, 0, up here we have the vector 1, 1. Over here we have the vector 1, 1. Over here, over here. We just fill in the plane with these vectors 1, 1 because every point in the plane has this vector 1, 1 associated with it. And again, it sort of fills the space. But in this case, instead of filling the space with values, it fills the space with vectors. Let's take another example. Let's say we have the function which maps to every point. It maps the vector y, x. So in this particular case, 0, 0, maps to 0, 0, and 0, 0 is a vector with no length. So that's sort of nothing. Nothing really happens at 0, 0. But let's say over here at 1, 1, or 1, 0. 1, 0 maps to the vector 0, 1, and the vector 0, 1 points up like this. What about at the point 0, 1? Well, that maps to the point 1, 0, and 1, 0 points off in this direction. And then if we go out, say, to 3, 2, out 3, up 2, 3, 2 maps to 2, 3, so it points sort of up like this. Negative 1 maps to negative 1, negative 1, which is, this guy looks something like this. And we get vectors that sort of point all over the place. Okay, if we fill it in, we can sort of start to see some patterns, but I gave a pretty weak sketch there. So what we're going to do is we're going to switch to a graphing utility. Okay, so back in Grapher, we take a point xy and we map to it a vector. And for this particular example, we were doing yx, and if I graph that, we get something that looks like this. And again, Grapher, what it does as a little trick is it scales the vectors all to the same size, but then color codes them. For the longer magnitude is a different color, and the shorter magnitudes are darker colors. So we get this shape. If we want to take a look at the original one we did, which was 1, 1, it ends up looking like this. We've got vectors 1, 1 pointing all at every point in space. Now again, these are not filled in at every point in space. There's space in between, but if we really did fill it in at every point, we wouldn't be able to make any sense of it. So we just leave some space so that we can see what's going on. Alright, that's how you graph a vector in a vector function from R2 to R2. Now you can do vector functions from R3 to R3. They get really complicated. I won't be asking you to do it by hand, but I think it is sort of instructive to see what those look like. So here, back in R3, we have a function. I just picked sort of complicated one just so we can get the feel for it. But here we've got vectors pointing all over the place in 3 dimensions, and again filling the space. And we see here there's something strange going on one of the axes. You can see that little space in between there where there should be some vectors. That has to do with the fact that y equals 0 is not in the domain. But you get the idea of what a vector field looks like. Again, we're taking a vector in 3 space, x, y, z, or a point in 3 space, and assigning to it a new vector which is determined by the coordinates.